Cool. So welcome everyone, and very happy to hold our first AI talks after CVPR. Hope you already have a good submission. And today we are very happy to invite Murtaza Dalal. He is a Ph.D. student at Carnegie Mellon University, advised by Ruslan Salakhutdinov. Sorry. So yeah, his his research is on machine learning for robotics, especially enabling robot agent to learn and perform non-horizon manipulation behaviors. So yeah, let's welcome Murtaza for his talk. And yeah, Murtaza, you can start.
All right. Thanks, Jinkang, for that great introduction. And I'm happy to be here. So yeah, let's just jump right into it. So today I'll be presenting some of our work over the last few years on inductive biases for learning long horizon manipulation skills. So imagine that you have a robot that you want to use to complete your day-to-day tasks. Maybe, as I imagine a lot of these people that are listening to this talk are wanting to do, have more time for research. Just kidding. I hope it's to do other things. Maybe you want to have the robot clean up your room by arranging things neatly on your shelf. Maybe you wanted to pack up your lunch into your lunch bag, or set the table in preparation for dinner. Now, these tasks involve complex interactions in the environment involving making and breaking contact, moving and arranging objects into precise arrangements, and most importantly, multi-step reasoning. Now, the sequential nature of these tasks makes them particularly challenging to solve. The probability of success of the whole task depends on a product of conditional probabilities. The probability of the first task, probability of the second task conditioned on the first, and so on and so forth. So you can imagine these are very challenging. So how have researchers approached long horizon manipulation tasks in the past? Well, the main workhorse from the robotics and planning community is task and motion planning. I'll go into more detail later on in the talk, but at a high level, TAMP involves reasoning over discrete sequences of primitives, task planning, while producing geometrically feasible action sequences, motion planning. On the other hand, from the learning community, people have approached the idea of long horizon robotics via the use of hierarchy. Hierarchy makes use of options, scene or task graphs, or explicitly designed transitions to address long horizon manipulation problems. Work on dynamic or probabilistic movement primitives also falls into this sort of category. We'll keep coming back to these approaches over the course of this talk, as our methods will leverage useful inductive biases from these camps to augment and accelerate learning. Now, I hope I don't have to answer this question for you guys, but I'm going to try anyways. Why learning? Well, there are quite a few advantages to learning. You minimize your task-specific engineering effort. You can operate over raw inputs, such as vision, point cloud, that sort of thing. And sort of crucially, the most important thing is the network's ability to generalize when trained on sufficient data. Now, our approach that I'm going to talk about in this talk is about augmenting learning with inductive biases inspired from robotics. How can we take lessons from robotics and use that to massively speed up our learning algorithms, to improve their performance, to generalize much better, and to fundamentally be able to solve tasks that we couldn't easily do before? So for that, we'll use motion primitives for reinforcement learning, which will be the first topic we'll discuss. Then task and motion planner supervision for imitation learning. And finally, LLM guidance plus contact-free motion planners, again, for reinforcement learning. All right, so with that, let's jump into the first approach, motion primitives for reinforcement learning. And this was work published at NeurIPS 2021. So taking a step back, let's ask the question, why is reinforcement learning so challenging for robotics? Is it maybe because rewards are hard to specify in the real world? Safety, hard to prevent the robot from damaging itself while acting in the real world? Or is it exploration, that the robot can't find the solution itself? Now, all of these are valid concerns, but the one that we're going to really focus on today is exploration. Now, exploration especially in the context of reinforcement learning for robotics, is very challenging because random actions almost never reach anywhere useful. This is due to the high dimensionality and continuous nature of the action spaces in robotics. Let me show you some examples. So if you just run random actions on a torque-controlled robot, this is sort of the behavior that you get. Now, if you run it on a joint angle controlled robot, you'll get something that looks like this. And finally, if you run it on something with a slightly more abstracted action space and effector control, you'll still get something that is largely dithering and does not very often actually interact with the environment itself. And for long horizon manipulation specifically, this is an even greater challenge, because even if the agent somehow manages to reach a region of interest for one subtask, the probability that it does so again and again for additional subtasks sort of decays as a product of those conditional probabilities and becomes very small very quickly. So what can we do? Well, a lot of the prior work in the RL community, at least, has been to improve the RL algorithm itself so that you can do more efficient continuous control. Initially, there was DDPG, then there was TD3, and there was SAC, and far more modern algorithms that exist today. On the other hand, folks have also tried to improve exploration over the raw action space via some sort of intrinsic motivation objective. So specifically, I'm referring to papers that do some sort of curiosity-based exploration. This hasn't been shown to scale particularly well to robotics just yet, but we'll kind of see as we go. On the other hand, an alternative way to approach the problem is to improve the interface of the RL algorithm with the robot itself. There's a ton of prior work in the hierarchical RL community on this, primarily on skill learning or primitive learning. As you can see here, there's a ton of approaches, and this slide is actually 2 years old, so there's probably a lot more since then. But the fundamental problem is that these sort of approaches don't scale well to challenging tasks. Generally, they require human demonstrations, which are fairly hard to obtain and very costly. So what are other approaches? Well, the idea of primitives is actually well explored in the robotics literature itself as well. Dynamic and probabilistic movement primitives are some of the two main types of methods that have been explored, but they require demonstrations and can sometimes be kind of brittle. On the other hand, task and motion planning literature uses primitives as well, but it does require access to some sort of privileged information and collision checking in order to plan. Ideally, we want to be able to run these robots with as few assumptions as possible. That's why we chose to do learning. So how can we take some of these ideas and integrate this into our learning pipeline? In our method, we propose robot action primitives, or RAPs for short, which at a high level, they're expressive, they're easy to define, they're task agnostic, and they're transferable across robots, tasks, and environments. And as you can see in these videos, they're widely applicable to a lot of different manipulation tasks and enable the robot to solve a variety of different challenging long horizon tasks. So let's dive into the details. RAPs are parameterized functions that execute a predetermined behavior based on their input argument. Basically, what this means is that they're a parameterized skill that the robot executes, and it's only a function of the robot's proprioceptive state itself. So they take in some argument, and I'll give an example soon enough. They use this to compute a target robot state, S star, for the robot to achieve, which is shown right here. And then they drive the robot's current state to the target state using an a primitive dependent controller and an error metric that's dependent on what the primitive is. So let's walk through an example. Lifting. So here, as you can see, the robot lifts just straight up in space. It takes in a delta Z for how much to lift the arm. And then over the horizon of HK steps, it just gradually lifts the arm. And I think a really important thing to emphasize here is that these primitives are just a function of the robot's proprioception. They are not a function of the environment. They're not object specific. All of that is abstracted away. What we'll see moving forward is that the RL agent itself will operate over the space of primitives and learn how to interact with the environment without having its action space have any privileged information or knowledge. And so the idea here is that exploring over the space of primitives leads to significantly more meaningful behavior than random actions. So how do we use wraps in RL? Well, as I said, what we'll do is we'll replace the action space. And the way this is done is that given an input image, we'll train a policy that outputs a categorical distribution over the primitives. And here are an example of 4 different primitives that the robot can execute. So we'll output a categorical distribution. From that, we'll sample which primitive to use. And then we'll also output a set of mean and variance parameters over the arguments for each function. And from that, we'll subselect what are the specific mean and variance parameters we want to use to then sample the specific arguments that we want to execute on the robot. So going back to the lifting example, in this case, what we did is that we sampled the lift primitive, and then we sampled a mean z and a variance for the z, and we'll use that to then sample a specific value for z, which is how much we want to move up. And then we'll plug that into our controller and simply lift the arm. So here's sort of an overall view of what wraps is doing end to end. I'll just pause here for a second just so that you can kind of take it all in. Okay, cool. Let's move forward. So now we're going to talk about how we're going to evaluate this. So for all of our experiments, we'll use only visual observations, which is, again, what we can obtain in the real world. Proprioceptive input, which is given from the robot's own API and only provided to the primitives and used for designing those controllers. And finally, sparse terminal rewards, which we'll use to train our system. A quick note about the evaluation metrics. So we're going to measure task success rate with respect to wall clock time and number of network updates. So in this case, since we're going to be comparing against a variety of different methods that have different action spaces with different control frequencies, different numbers of low-level time steps per action, it's going to be very challenging to come up with a single metric to evaluate all of these. So instead, what we opt to do is pick 2 metrics, wall clock time, which is a good measure of how quickly an agent will solve the task, and number of network updates, which is a good measure of the scaling properties, like how many gradient steps do we actually need to solve the task. And between these two, we'll get a rough estimate of how do these different action spaces compare when training reinforcement learning agents. In terms of our evaluation environments, we evaluate on 3 different environment suites: MetaWorld, Kitchen, and RoboSuite, which contain a variety of different challenging manipulation tasks. So first, we test across all the tasks in our suite, and we try to evaluate if different action parameterizations, such as end effector control, which is shown in orange, and vices, which basically outputs the parameters of the end effector controller alongside the end effector commands themselves, can outperform wraps, which is shown in green. And what we find is that across every environment in every domain, wraps largely outperforms the baselines. We're able to very quickly learn to solve every single task, and we're able to do it much more efficiently than a lot of these prior works. Now, even if we allow the baselines to use dense rewards, which is shown in the dotted line, they still cannot match the performance of wraps. Now let's compare against some of the prior work that's more relevant to our direct method, which is skill learning. So we evaluate against state-of-the-art skill learning methods, Spiral, Dine, and Parrot, which use demonstrations to learn primitives. And on the easier tasks, these methods can somewhat match the performance of wraps, at least on kettle and microwave and slide cabinet. But as we increase the difficulty of these kitchen manipulation tasks, from light switch to top left burner to hinge cabinet, we find that wraps is the only method that really is able to learn to solve the task. And this is largely because these demonstrations that are used to learn those primitives aren't always, perfect, may be hard to fit to, or just in some cases may not be enough to learn the effective skills. Now we get to the setting that we actually really cared about from the very beginning, which was multi-step manipulation or long horizon manipulation. And in this sort of regime, we find that we can actually effectively chain primitives together to solve these tasks, solving 3 or more subtasks by the end of training. And these are all in the kitchen environment, where it needs to open the microwave door, push open the slide cabinet, flick the burner. But as you notice, and this will become a little bit more salient later on in the talk, a lot of the behaviors themselves are somewhat unintuitive and somewhat unnatural. And this is largely because of that the method itself uses a set of parameterized primitives, which have a specific type of behavior when executed in the environment. So the policy needs to work around how exactly it needs to operate. So what are the takeaways? Well, if you use the right set of primitives, in quotes, you can actually dramatically improve the efficiency of reinforcement learning. And here, these primitives are simple, hand-designed, but also very general. They're able to work across many robots, many different settings. As we even showed in our experimental results, we have 2 different types of robots. If you look in the paper, we actually show transfer across tasks, domains, and robots, which is sort of the next main point, which is that primitives based on the end effector state and actions are highly transferable. Finally, and this was sort of a point made clear from the results, existing skill learning methods are not learning the type of skills that we really want, while also requiring a significant amount of demonstrations, potentially in the thousands, which is, again, very costly to compute. All right. So let's move forward. Now we're switching gears a little bit and trying to answer sort of the reverse question from the previous work. So assume that for the agent, the high-level plan is more or less given or fixed in terms of the data distribution that you train on. Can you learn to solve a wide array of tasks purely from visual input? This was work done at NVIDIA and published at Coral this year. So now, as we've seen very recently, large-scale models, mostly transformers, trained on very large-scale data sets, equate to basically very powerful agents that can generate volumes of text from prompts, provide useful ranking and embedding features across a variety of different tasks, generate useful code, realistic images, pretty much whatever you can think of in a virtual domain. And these models are very powerful. And sort of the recipe here, as I said, has been large models, highly expressive, and very, very, very large data sets. So now you might ask, why haven't we been able to do the same in robotics? And sort of the answer maybe is kind of evident. Data, right? Data is the core bottleneck. There's a severe lack of useful data in robotics in the form of successful trajectories. And specifically, what type of data do we need for robotics? We want task-relevant data, and we need it to be diverse. We can't simply have the same task over and over again. Now, why is it hard to get? Well, robotics involves real-time online interaction, which is very, very hard to scale. In many of the cases, for example, RT1, RT2, which are sort of the salient examples in the literature, the data sets that were collected there required years of effort with many humans, probably millions of dollars, and it's difficult to scale potentially. So in this work, we're going to consider a very different type of data source. Rather than humans, we're going to consider task and motion planners as a data source in of itself. So let's go into a little bit more detail regarding what TAMP is and why it might be a good data source for robotics. TAMP involves simultaneously planning a discrete sequence of which objects to interact with, how to manipulate them, and continuous motions that safely and correctly facilitate these interactions. So it sort of assumes knowledge of the scene geometry, cost function for the task, and predefined action primitives. But then it can solve very long horizon tasks because the task planning component itself allows it to reason about events far into the future, while simultaneously reasoning about the low-level geometry of the task that it's considering. And so here's sort of what an example plan from a TAMP system might look like, where you want to pick up and place a cup onto a different rung of a shelf. And so you sort of move towards the cup, you grasp it, move to the target location and place it. So this is what TAMP is. And TAMP is powerful because it can solve these long horizon tasks that we care about. And it is also quite general. We're able to automatically apply it to many different scenes and many different environments. Let's quickly describe some related work in this area. So there's this work from Coral 21 by McDonald et al. Called Guided Task and Motion Planning, which essentially tries to distill a task and motion planner system directly into a neural network. Now, the core differences between this and what we're going to talk about today is that in our system, in our work, we're focused on training visual motor control policies, so going from vision to actions, which is a more realistic scenario that we actually will be able to use when deploying robots. And we want to really move away from using privileged information, which is what the guided TAMP paper leverages for its work. They also propose a hierarchical policy, which requires access to additional information that is not present at test time. And in contrast, sort of our system will use pretty much no additional information and just directly learn behaviors end to end. And finally, what we're going to do is really try to analyze this problem and understand what are the sort of challenges when imitating TAMP, and how can we actually use this as a data source for training large-scale models for robotics. So now what is our system itself? Well, we call it the offline pre-trained TAMP imitation system, or Optimus for short. And to give a high-level overview, what this system tries to do is first generates vast amounts of demonstrations on a diverse array of tasks by procedurally generating scenes and then solving them using TAMP. Next, what we find is that we need to adjust the TAMP data to make it easier for the imitation system to actually fit to it. Finally, we'll perform large-scale behavior cloning and deploy the policy on the robot. So let's walk through each of these steps in a little bit more detail. So for procedural environment generation and TAMP solution, first, we're going to generate a wide and diverse array of environments, which are visualized here. These procedurally generated environments cover tabletop pick and place, shelf object manipulation, articulated object manipulation, with over 72 different objects, which are chosen from ShapeNet. And then we also randomize the object poses, the sizes of objects, and the sizes and shapes of the scene obstacles themselves. So this will create a diverse data set for our imitation learning system to fit to. Now we'll use the TAMP system to actually directly solve these tasks. And the nice thing about TAMP is that in simulation, we're sort of able to just automatically generalize across a wide distribution of tasks with a simple goal specification. In this case, we'll use a specific TAMP planner, PDDL stream, which optimizes a planned skeleton sequence of parameterized actions and its continuous parameters and paths to execute those actions. Uses sampling for grasp generation, placement sampling, inverse kinematics, and motion planning. One of the interesting things is that TAMP produces very multimodal trajectories. And this is primarily because of, well, the sampling algorithms that I just mentioned. So the grasps are randomly sampled from the acronym dataset. The placements are randomly sampled based on sort of the receptacle. The inverse kinematics itself is a bit random as well. And the motion planner is random because it's using a variant of RRT. And so what this results in is highly multimodal trajectory distributions, which for the same exact pose, environment, scene configuration, everything, will actually have wildly different behavior. And this is very challenging for imitation learning systems to fit to. And because most likely what we'll end up doing is fitting to some sort of average. And we'll address sort of on the learning side how to handle multimodality, but we can actually take some steps on the data side itself to reduce the multimodality and make it easier for the imitation learning system to fit to the data. So specifically, what we're going to do is reduce the multimodality by optimizing for low-cost plans rather than simply feasible plans. So the TAMP system just cares about achieving the goal, but now we'll also modify it so that it gets ideally the optimal path to the goal as well. And this is simply a change to the objective function for the motion planner to lower the trajectory length. Simple solution. We'll also limit the variability in the IK solutions themselves. So we'll seed the IK from a specific seed, and which is the initial configuration, and we'll optimize for the closest solution within some timeout. And this, again, reduces the multimodality, making it easier for the imitation learning system to fit to the data. So now that we've generated our data, we need to transform it and filter it to, again, maximize learning performance. So one of the big issues for training visual motor policies from TAMP data is actually that TAMP generally plans in joint space, and it's fairly difficult to train behavior cloning from images to joint space actions. The reason for this is that the network essentially has to not only learn the policy, but also learn the camera projection from pixels to poses, and then the inverse kinematic mapping from poses to joint angles. Instead, what we opt to do is use task-based control. And there's a simple way of doing this. Just use forward kinematics on the waypoints outputted by the TAMP system. And this transforms them from joint space to end effector. And then we'll track these with an end effector controller. Next, when imitating a privileged expert, such as TAMP, which operates over privileged information, it's fairly challenging for the policy to know why the TAMP system made a specific decision if it cannot perceive it. So to kind of address this issue, we offer a couple different solutions. One, the policy should take in a history of observations. Secondly, it should use a wrist camera, which improves its ability to perceive scene geometry. And then finally, we use multiple well-tuned camera views, which offer, I guess, easy to see or I guess nice observations of the environment itself. Finally, we need to filter the demonstrations, again, to try to reduce multimodality. So if we have highly stochastic randomized planning algorithms, then we'll find that some of the trajectories can be very out of distribution. And those trajectories increase the likelihood of compounding error. And there's a simple and intuitive reason for this. So if you have a mean set of trajectories in your data distribution, and you have some that go slightly further out, and your network fits to both of them, then there is a chance that it might, on some actions, go slightly outside of the sort of standard manifold of things that it's seen, and then continue to make mistakes once it's out of the region of things where it knows what to do. So we have a simple solution. We prune the data using two rules. One, we remove outlier trajectories that have length greater than 2 standard deviations away from the mean trajectory length. And then we also prune out trajectories where the end effector pose exits the visible workspace. Finally, let's quickly describe the policy architecture that we use to perform large-scale behavior cloning. Specifically, we use a transformer model that operates over just the history alone. And for each time step, we produce one token, which is a modality, which integrates information from all the different modalities and all the different types of observations that we see in that specific time step. So what I mean by that is that for a specific time step, for each image, we'll encode it using ResNet, or for proprioception, we'll encode it using an MLP. We'll project all of these, we'll concatenate and project all of these into the transformer embedding dimension, and then we'll simply attend over these tokens. And what we found was that using a short context length is crucial in order for the transformer model to not overfit to its own mistakes. So in our paper, we use a context length of 8. Another thing that was really important is that when you train this model, in order to handle multimodality, you need to have an expressive output distribution. So specifically, we use a Gaussian mixture model with 5 components, and this ends up fitting quite well to the multimodal data that we observe. Again, I want to emphasize that we're fitting to the raw actions in contrast to a lot of prior work for transformer imitation learning, which fits to some sort of discretized representation. So for evaluation, we evaluate on a wide set of tasks that really test our different aspects of our manipulation system's capabilities. And we evaluate long horizon manipulation with simple objects. So you have block stacking on the left, objects with potentially varying geometries. So this is like pick place shown in the middle, manipulation of objects in the presence of 3D obstacles. So you have shelf right here, or articulated object manipulation, which is a microwave task here. And then we also include single and multi-object variants of each of our data sets to evaluate massively multitask model learning. So these are data sets with up to 72 different objects. And I want to note that each of these data sets includes thousands of demonstrations, which we're able to very rapidly collect because we're using a task and motion planner instead of having a human collect the data manually. Quickly describing the evaluation protocol. For baselines, we compare against behavior cloning with an MLP, with an RNN, and also behavior transformer, which is a specific type of transformer designed in prior work. For single task results, we'll use 30 million parameter models, and for multitask, we'll use 100 million parameter models. The evaluation metrics are task success rate. So with that, let's start looking at what we got for our results. So what we find is that Optimus produces closed-loop reactive policies capable of solving over 300 long horizon manipulation tasks with up to 72 different objects and 8 stages. Optimus also trains policies capable of solving multi-stage manipulation tasks, which require the network to learn to fit a variety of different behaviors, getting up to 60% success rate on this challenging task, again, from low-level control. In terms of numerical results, we find that Optimus largely outperforms the baselines, is able to solve very challenging tasks like 5 block stacking and 4 object pick and place with fairly high success rates, especially compared to the baselines. We also find that Optimus can solve tasks requiring obstacle awareness, learning to grasp and then place the object in the middle rung. Optimus can also solve tasks requiring pick and place, or skills beyond pick and place, learning to manipulate articulated objects, and again, solving the microwave task with 86% success rate. And as we see here, on tasks involving many different objects, our system is also able to, again, solve the task with high success rates, with multitask results getting in the 50 to 60% range. Again, largely outperforming the baselines. Finally, we show that Optimus can also distill TAMP's task planning capabilities, learning to clear the area in front of the microwave before opening the door and placing the cup inside. This means that it's able to actually end-to-end absorb some of TAMP's planning capabilities. Now for a slightly cool comparison, we find that Optimus actually can outperform the TAMP supervisor itself, being much, much faster to execute, 5 to 7.5x. And the policy performance actually improves over the supervisor by 30%. So you might be wondering, how can the student improve so much over the teacher, or in fact at all? Well, we hypothesize that the higher success rate is because Optimus learns from successfully executed trajectories, enabling it to account for dynamics, which TAMP does not during execution. Optimus is essentially learning a very good filter. Let's jump into what we learned from this work. We find that TAMP supervision enables broadly capable visual motor policies that are able to solve like up to 70 different tasks with a single network, with full low-level control from visual observations. We also find that careful data distribution is very crucial to imitation learning success. You need to be able to design your data in a way that's easy for networks to fit to. Finally, transformers are effective long horizon manipulators, which we found in the pick and place results, and also highly capable multitask learners, which is what we saw in the multitask results. And with that, we get to our final approach, using large language models and contact-free motion priors to accelerate reinforcement learning. For this, I'm going to cover Plan Seek Learn, which is work that is currently under submission. So let's go back to those challenges that we described earlier for long horizon robotics tasks. These tasks, as I said, require complex interactions with the environment, and the probability of success is fairly low because it's dependent on these conditional probabilities. Now, in terms of the way that prior work has addressed this, on one hand, we have classical methods, which can perform long horizon reasoning, but require privileged information and still struggle with contact-rich interactions. So as you see here, there's a TAMP system that's able to do simple pick-and-place operations, but that's sort of the extent of the sort of problems that TAMP systems are capable of handling. On the other hand, we have end-to-end learning methods, which can solve very challenging dexterous manipulation tasks, very complex behaviors. However, in general, they struggle to learn without having sufficient dense reward guidance. So exploration, as I mentioned in the first paper, is a core challenge to end-to-end learning. Now, finally, let's talk about a more recent solution to solving long horizon tasks. Maybe something that you're wondering why I haven't mentioned yet. Large language model planning. Large language model planning methods can effectively solve tasks zero shot without privileged info, unlike classical planners. But in many of these cases, they require pre-trained skill libraries. So here we show SACAN on the left, text to motion, and prog prompt as some examples of such methods. But by and large, these sort of methods require some sort of pre-trained library or some sort of predefined library in order to be able to execute their motions. And sort of the question that arises then is, well, what if a pre-trained library is unavailable or hard to obtain? In certain robotic settings, it might be hard to obtain these sort of skills a priori. Dexterous manipulation is one good example of this. And maybe another question is, what if we wanted a system that could improve with data online? Currently, these sort of methods simply perform some sort of text-based planning without adapting the skills at all. And ideally, we would want to either improve with data at the low level or at the high level. And currently, these approaches aren't really able to do either. So as I sort of said, ideally, we want LLMs to guide the learning or guide policies to learn to pick up new skills. And we want them to improve with data. Now, the question becomes, how do we connect coarse, high-level language planning to low-level control, which are very disparate, very different? Now, the sort of naive solution is to do some sort of language model plan with a language conditioned RL policy. This is sort of the SACAN style approach, but this requires pre-training, and you need to have those skills a priori. Ideally, we would like to have an agent that can leverage the strengths of all of the methods we've discussed before: language planning, classical planning, and learning, to obtain an agent that can solve challenging long horizon tasks with as few assumptions as possible. And so to that end, our solution is to use vision plus motion planning as a way to step through the language plan and to learn local control policies using RL along the way. Motion planning allows you to ground the language plan in the robot scene and enables the RL policy to only focus on the challenging parts of a robotics task, which are the environment interaction stages. The rest, we have a strong set of tools that are able to get us pretty far. So let's look at our method at a very high level. Basically, what it does is that it uses an LLM to decompose the task into a coarse, high-level plan, which is shown here. Then it uses vision and motion planning in the sequencing module to step through the plan and essentially initialize RL policies which are learned in the learning module, to efficiently learn local environment interaction. We will now go through and describe each of those components in a lot of detail. So let's start with the planning module, or zero-shot high-level planning. We need plans that can be interpreted by the sequencing module, which is a vision-based system that produces and achieves robot poses using motion planning. So in order to do this, we have the LLM predict a target region, which is a natural language label of an object or receptacle of the scene, which can be translated into a target pose to achieve at the beginning of each stage of the plan. And we also introduce stage termination conditions. Basically, what these are exit conditions for some sort of skill. So for example, grasped, placed, and opened. Those are some examples that we use. Crucially, we only need to define a verification step, estimating that this sort of skill is terminated, not predefining the local low-level behavior that you need in order to do that skill. That is what's difficult. So how do we run this? Well, simple LLM scheme. We use a prompt that describes the task, the conditions, the objects, some sort of formatting for the right output that we want. And what we found was that for the LLM, GPT-4 works the best. We found it got 100% planning success rate across all of our tasks. And we tried a variety of different other LLMs in initial testing, GPT-3, 3.5, 4, Llama 2. And by and large, those models tend to either not adhere exactly to the task description or hallucinate objects or some other sort of issues. So moving forward, we stick to just GPT-4. So here's sort of an example of the prompt as well as the plan that we use for a specific task, the nut assembly task. Right. I hope you were able to read that at the speed at which it was coming out. But as you can see, the plans themselves, or sorry, the prompts are very simple. And now what we'll see is what the plan is outputted by the language models. So the plan itself is also very coarse, but it decomposes the task in a way that makes it easy for the agent to learn to solve exactly what it needs to do. So moving to the next part of the method, the sequencing module. The sequencing module takes in the target region, estimates its pose, and then motion plans to that target location. So the inputs are the target region, the global views of the scene, and the depth images. So by global, we mean that you can see essentially everything. And we have multiple views, which we visualize one right here. And these are used to just cover whatever's happening in the scene. We segment the region using a pose estimation system. In this case, the way we implement it is using calibrated depth and segmentation, specifically SAM. And this allows us to have a natural language condition pipeline to mask out the object of interest and estimate its pose by averaging the points in the point cloud that correspond to that object. So we use this to compute a target end effector pose near the object. We pass this to inverse kinematics to get target joint angles. And then we run AIT star, which is a variant of our T star, to achieve the optimal target configuration near the region of interest, or to achieve an optimal path to the target configuration. And here's sort of a visualization of the robot arm getting closer and closer to the can. Finally, once the sequencing module puts the agent close to the target of interest, we train RL policies to interact with the scene by optimizing the task reward. We make 3 changes here to maximize learning performance. One, the RL agent is trained with just a single policy across all of the different stages. This allows the agent to share the value function and adapt its behavior according to different stages. 2, the stage termination conditions, which we mentioned a priori, which prevent dithering behavior. Finally, we use local observations instead of global observations, which our agent is uniquely capable of learning from because it is already initialized in a local region near the object and only needs to learn a small bit of interaction. And this greatly improves learning speed, as you can see in the paper. So here we also just visualize like what does a placement policy look like from the view of the RL agent itself. So here's a full pipeline example, which we'll walk through very quickly. So given the LLM and the prompt, we output all of the different steps of the plan, which we've seen before. Here's a visualization of all the intermediate poses. This is after executing each of these sub-steps. Zooming into a single stage of the process, going from O1 to O2. We start with the nut grasped, and we estimate the position of the peg, which again is given to us from the language plan. Then we motion plan to right above the peg. And then we execute the local control policy and learn to place it on the peg itself. So just to recap, we use the large language model plan to perform coarse high-level planning. We use pose estimation and motion planning to step through the plan. And then we initialize the RL policy close to the regions of interest and train local RL policies, which solve the interaction component of the task. I'm going to quickly jump through our experimental setup and start talking about the results. So we compare against a variety of different baselines, which have hierarchical RL, motion planning, task and motion planning, SEICAN. We train with visual observations, the original task reward, so we don't modify it at all, and description of the task in natural language. So let's move on to the experimental results. So we find that PSL, or planned sequence learn, solves 25 plus long horizon robotics tasks across 4 benchmarks: RoboSuite, MetaWorld, Kitchen, and Obstructed Suite, with greater than 85% success rates. We also find that PSL is able to solve tasks with obstructions by leveraging motion planning. So here, the motion planner moves the robot to an unobstructed configuration, and then the agent is able to easily place the peg in the hole. And again, I want to emphasize there's no privileged information given to any component of our system. All of this could be run directly in the real world if desired. So here are some results and some learning curves on the single stage tasks. And we find that our method in green is the most sample efficient in most cases. Some cases it is similar to performance of the end-to-end learning methods. And sort of the important part here is that these are just single stage tasks where all we're doing is initializing close to the object, and that already gives us a very big benefit. Now what we'll see is that for long horizon manipulation, which is sort of the regime that we really care about, our method greatly improves the learning performance, to the point where we can solve tasks that could not be solved by some of the prior methods. So here we see PSL learns long horizon behaviors with up to 5 stages and diverse interactions, from pushing the kettle to opening the microwave door, to turning the knob, to flicking the light switch and sliding the cabinet door. So in terms of the results, we find that PSL has very strong results, able to solve up to 5 stage manipulation tasks, as we showed. And crucially, strong baselines such as TAMP and SEICAN actually end up failing once the number of stages goes up really high. This is largely due to cascading failures during execution. Small mistakes during execution leads to failure, since these systems do not learn online. So overall takeaways: large language model guidance enables the RL agent to focus on the hard part of the task for control. And the semantics and task decomposition can simply be handled by a large language model. Find that motion planning grounds the LLM plan in the scene and allows it to naturally step through the plan. And as I mentioned sort of time and again, Control need only be learned at a local level for contact-rich interactions. So now let's quickly summarize what we learned today. So for RAPs, RL for high-level decision-making, motion primitives for low-level control equals fast and efficient learning. Optimus, TAMP supervision paired with transformers enables capable long-horizon visual motor policies. And finally, with PSL, large language model planning guides RL using contact-free motion priors to get the best of high-level planning, motion planning, and reinforcement learning. And as sort of noted below, for more information on all of these works, please do check out my website. With that, I want to do the customary collaborator thanking, folks at NVIDIA, as well as folks at CMU that I've worked with over the past few years and have been great for advice, mentorship, and pretty much everything, especially my advisor, Ruslan Salakhutdinov. And so with that,